Okay, so in chapter 3 in general, we go over a lot of, I don't know if that's the right word to put it, but more complicated mathematical stuff. Like it's stuff that gets focused on a lot more in the traditional Calc 1 sequence. We're covering it in this class really because we want to talk about derivatives, which is a major part of calculus. But in order to talk about derivatives, you need to know a little bit about limits. And that's what a lot of chapter 3 is. We're just trying to sort of um, give an introduction to what limits are. So I'm going to use this example from the homework to try and talk about that a little bit. So there is first some notations that I want to use here. So I'm gonna look specifically at which points do I want to look at here? Probably let's start with analyzing -3. Okay, we're looking about that point on the graph. So one thing is that there's a hole there. And so if we just tried to, let's say if this is representing our f of x function, if we tried to evaluate something like f of -3, we would say that it's undefined. The thing about limits is that it can be undefined, but the limit can still exist. And so the limit notation is written like this. So there's a limit as x goes to -3. So a little arrow and then a -3. We can also look at limits from a left and right perspective. So I'm going to start by left. So that's what it looks like. So this is read as the limit as x goes to -3 from the left. So the extra negative at the end of the number is saying from the left. So what does that mean? That means if we travel along our graph, getting closer and closer to -3, we want to see where are the y values heading towards. And the y values are heading towards -2. So the answer is -2. If we do the same thing, the limit as x goes to -3, but now let's look at it from the right. Now we're going to start to the right of that point, x is equal to -3, and we're going to travel along our graph, getting closer and closer to x's -3, and as we do that, we can see that the y values are going towards -2. So that answer is the same in this case. And now let me put on here, I'll just move over to the left here. So what about now if I wrote it as, sorry, I know it's a little bit crowded looking, x goes to -3 of f of x. So what if you don't have that little extra plus and minus? What that means is the limit as x goes to -3 is that if you look at from both the left and the right, what number is it going towards? And we've already analyzed that. We said from the left it's -2, from the right it's -2, so it's going to be -2. In this case, they're all the same. Okay, now let's go ahead and do the same thing for x equals -1 on this graph. So I'm actually going to go ahead and erase all this. Now let's look at x is equal to -1. So first let's try to figure out f of -1. So if we just plug in -1, what would be our y value? So at first you might look at this and say, oh, it's not defined because there's an open circle there. But let me change colors here. Think about this vertical line here as all the places where x is equal to -1. The graph actually is defined at -1 because there's another point that crosses that point -1, and it's down here. So that answer is that f of -1 is equal to, what is that, -5, which is the same as saying that this is a point on the graph, -1, -5. Now let's look at the limits. So the limit as x goes to -1 from the left means we travel along our graph from the left of that point. So in this case, we'd have to go to this part of the graph, and as we travel along, getting closer and closer to x is equal to -1, our y's get closer and closer to -5. So that's the answer. So now let's look at the limit as x goes to -1 from the right. So now I need to jump to the other graph. And I travel along, I want to get closer and closer to x is equal to -1. And the y's, as I do that, the y's get closer and closer to -2. And so now what about the limit as x goes to -1? Which means we have to look at both directions. All right, so I'm going to squeeze this in over here. So the limit as x goes to -1 of f of x. Well, we said from the left it goes to -5. From the right it goes to -2, and those numbers are different. Because those numbers are different, we would actually say that the limit does not exist. Does not exist. And sometimes that's abbreviated as DNE. So if we go back and look at our graphs, we kind of can tell just from this graph that there's something strange happening at both, x is -3 and x is -1. But in terms of the limits, there's something different happening. So here, yeah, there's a hole in the graph, but essentially on either side, it's going towards that same point. So that limit still exists. Where there's this big gap over here at -1. So if that happens, then the limit does not exist. So that's one thing that's covered in section 3.1. And again, what I'm doing right now, I would call like a micro lesson. So if you're still confused and you're like, I don't know what she's doing, it's okay. Make sure to go ahead and watch the full lecture video that's in my lab, and then read the ebook, and then and look at the extra resources as well. And of course, contact me if you still have questions about it. All right, so there's one other thing I want to look at from this homework. Evaluating a limit like this. So to evaluate a limit as x goes to -5, if you're given the function, you can actually just plug in x is equal to -5. And if we do that, we get -5 squared minus 25 over -5 plus 5. And we get 25 minus 25 over -5 plus 5, which is 0 over 0. So 0 over 0, mathematically speaking, is something special, I guess, in terms of it being different than if you had ended up with something like, if you ended up with something like a 5 over 0, we would just say it's not defined and the limit does not exist. But the 0 over 0 actually tells us that there's going to be a hole in the graph, just like if we went back to that example we had just done from the homework. It tells us that something like this, what happened at x is equal to -3, is happening with our graph. So that means it's not defined there, but the limit does exist. So we need to do a little bit more work to simplify so that the limit does exist. And in this class, we're going to look at 3 different ways to simplify. One is factoring and canceling. One is getting a common denominator and canceling. And then the third is multiplying by the conjugate, which is something that you do for square roots. I'm only going to go over, just to kind of illustrate a little bit, the factoring one. All right, so here let's use the factoring technique. So if we try and simplify, x squared minus 25 is the same as x plus 5 over x minus 5, all over x plus 5. The x plus 5's cancel, so it actually simplifies to x minus 5. But there's going to be a hole in the graph like what we saw over there at x is equal to -5, but that does not affect the limits, which means now that we simplified, right here, we can just go back and plug in the point we were originally trying to plug in, which in this case is -5. So we end up with -5 minus 5, which is -10. And that's our answer. Okay, I alluded to the other ones, but just to show you like 9 in here, this is one where you'd want to get a common denominator first and simplify from there. This is the example where we do something called multiply the conjugate. Those are two other simplifying techniques that we're going to do in this section. Okay, so now looking ahead to just a kind of brief overview of section 3.2, some of the questions I think on the homework can look very confusing. Like number 2 here that has many different options to choose from. So this is actually trying to talk about discontinuity, which is a matter of if the limit exists or not. Really what you need to look for if you're looking for where it could be discontinuous is you're looking at the denominators. So right here, it's not defined at x is equal to 0 or x is equal to 7. And I check and nothing simplifies, like I can't cancel it out with anything in the numerator, so I'm stuck with those. Those are actually both points of discontinuity, and the limit does not exist there. So let's see, what option would that be? Single value, two values. This would be an example of what this is trying to say. So it's discontinuous at 2x values, so in this case it's 0, 7, and the limits do not exist. And then compare that with something like this, which is very similar to the other function that we tried to simplify in section 3.1. This one, there's going to be a point of discontinuity at 6. We just don't know what kind. What makes this different from the other one is that it actually cancels. And so if we try and simplify, x plus 6, x minus 6 is how the top factors over x minus 6. It's saying that this is basically the same function as x plus 6, but it is undefined for that point 6. So there's a discontinuity at one value. So if you look through all of these options here, it's saying it's discontinuous at a single value. So the limit does not exist would be similar to the last problem, but since it cancels, that's not the option. So it's actually going to be the first one. So it's discontinuous at 6, and the limit is, well, we talked about from the last section that to find the limit, we just go and plug it back in once we simplify it. So we can go ahead and plug that point in. So it's 6 plus 6. And so in this case, the answer is 12. And then I'd like to look at the last one too, because again, I do feel like when you look at these homework questions at first glance, they look very intimidating. This one doesn't have any denominators, so there's really no issues here. So this one's just, it's continuous everywhere. There's no points of discontinuity. So we just have to find that option. There it is. F is continuous for all values of x. Okay, so again, a very short intro to what you're going to be seeing this week.